All right, in this video for limits, this is the second section of our limits unit, is on continuity and one-sided limits. So two topics, continuity and one-sided limits. All right, first, in mathematics, the term continuous has much the same meaning as it has in everyday language. Informally, to say that a function is continuous at x equals c means there's no interruptions of the graph at c. So that is basically saying that the graph is unbroken at c. No holes, no jumps, no gaps, no vertical asymptotes. Here's a couple of examples of exactly what I'm talking about. Interruptions, places where the graph is broken. In this first graph here, we have a hole, right? So the graph is broken. It's not even defined. At f of c, it does not exist. There's nothing at f of c, and that creates interruption in the graph. You could think of it as if I wanted to draw this graph with my marker, I would have to lift it up and come back on the other side and keep going. So I had to lift up my marker. There was a break. There's an interruption. That is where the graph is not continuous. Here's another example of a not continuous. We call this a gap or a jump. And this is where, I'm drawing it, and on the left side, I'm up at this value, but then boom, on the right side of C, I'm over down here. So again, this is an interruption. Here, the graph does exist, okay? If I go back here and erase, you can see that the function does have a point at C. There is a filled in dot right here. So the graph does exist at C, but the limit does not. The left side and the right side do not come together, so therefore the limit does not exist. That's going to be a break or an interruption. Here's another example. We call this a displaced point. This is much like a hole, but instead of throwing the hole away, I just move it down. So here, if I'm going to draw this, I'm drawing it, and then I got to lift up my marker, got to add this point here, and then come back on the other side. So in this graph, there is a point at C. It's right down here. And the limit does exist at C. It's somewhere up at this value right here, but those two values are not the same. That's going to produce a break or a graph in the graph. Now there's one more example I could draw. I didn't. I'm just going to draw it real small, and that would be a vertical asymptote. If I had a vertical asymptote, when I go ahead and draw my function, it's going to come in here and shoot straight up, or maybe it'll come down here and shoot straight down. The point is that that's clearly a break, right? In that particular example, I do not exist at C, nor does the limit exist at C. So that violates many things. So essentially, there are three different ways that continuity can be destroyed. If the function does not exist at C, then you cannot have continuity at C. If the limit does not exist at C, or as you approach C, you cannot have continuity at that point. And if the limit does exist, but it's not equal to where the function exists, you also will not have continuity. So in that third example, you might have a limit that exists, you might have a point that exists, but if they're not the same, you're not going to have continuity. So the only way to truly be continuous is to meet all three of these conditions. All three have to be met. So first, you must be defined at C, meaning that when I plug C into the function, I need to get a defined value. I cannot get does not exist. Second, the limit has to exist as I approach C. So as I approach C from the left, as I approach C from the right, I have to be approaching the same number. I have to be existing. My limit has to exist. And the third condition is that the answer to 1 and the answer to 2 have to be the same. So whatever happens when I plug C into the function must be equal to the limit as I approach that function. If those two numbers are equal, then I do exist. All three of these must be true. So let's look at this example that we saw earlier. Why is this not continuous? Well, because condition 1 fails. Condition number 1 says that when you plug C into the function, you have to get a number. You have to get a defined value. Well, sorry, it does not exist. Nothing happens at C. So here, the condition 1 fails. Now, I don't even have to check any of the other conditions if the first one fails, but it is worth noting that the limit does exist at C. It exists somewhere right here, but sorry, it doesn't matter. Since the function already doesn't exist, I cannot be continuous. Here's another example, and in this case, let's check the first condition. What happens at C? Well, I am defined right here. At C, there is a defined value right there, a filled in dot. So that condition passes. But number 2, the limit as x approaches C, sorry, this does not exist. The left side is up here, the right side is down here somewhere, the limit does not exist. So I'm not even going to go any further. This clearly is not continuous. And here's our third example. Let's go through our conditions. First, do I exist at C? Yes, there is a point at C right there. I definitely exist. That function, or that condition counts. The second condition says, is there a limit as x approaches C? Absolutely. As I approach C from the left, as I approach C from the right, there is a limit somewhere right around this value right here, and that does exist. But the third thing is that those two previous answers are not equal, right? Where the function exists is not equal to where the limit is as I approach C. And this is what creates a discontinuity as well. Now, if we go back to that other example that I kind of mentioned, which is a vertical asymptote fails condition 1 and 2. Sorry for my bad drawing. So here, not only do I not exist at C, but my limit does not exist. So I violate condition 1 and condition 2 in a vertical asymptote. So that's another example of a break. So what does a graph look like that is continuous? Well, here it is, right? Look at this beautiful graph. I could draw this whole graph without ever lifting up my marker. This is a continuous graph. Let's just check that it is continuous at 1. All right, here I am right here at 1. So first, does the function exist at 1? Yes, it looks to be at a y value of 1. Does the limit exist as x approaches 1? Well, yeah. My point is coming together from the left side, from the right side, and it looks like I'm coming together at 1. And the third condition says that those two answers must be equal. So yes, I am successfully continuous. And that would be true for any point on this graph. So this graph is continuous throughout the entire graph. All right, so now that we know a lot about ways to be not continuous, or another word for that is discontinuous, we have two different types of discontinuities. The first type of discontinuity is removable. To make sure that you know that you have a removable discontinuity, first and foremost, the limit does exist, but there is a hole or a displaced point. So this is a good example of this. If you look at this point right here, I know it's super tiny, but that right there is 2. At 2, the limit does exist. The limit exists, first off, the point exists up at 4. The limit exists at 2 as well, but there's a hole, or in this case, a displaced point. This is what we call a removable discontinuity. I literally took a point and I removed it and either threw it away or put it somewhere else. But the important part is the limit does exist at 2, but there's a hole there. That's called a removable discontinuity. The opposite is pretty simple to remember, a non-removable discontinuity. Here, the limit does not exist. This is because of either a vertical asymptote or a jump gap. For example, if we look right here at this particular value, I don't know, maybe that's x equals 0.2, looks like. The left side goes up at 1, the right side is down at -1, therefore the limit does not exist. So that's not a hole, that is just a jump gap is what I call it. So again, that is a non-removable discontinuity. So the limit does not exist, and it's discontinuous. And here's an example of a vertical asymptote at this particular value, 1, 2, 3, 4, 5. So at x equals 5, the function doesn't exist, the limit doesn't exist. That's obviously a discontinuity, and that is called a non-removable. So if the limit exists, it's removable. If the limit does not exist, then it is non-removable. And basically, graphically speaking, that's a hole for removable versus an asymptote or a jump gap for a non-removable. All right, so let's just take a look at a couple examples here and talk about the discontinuity of these functions. So if I were to ask you, look at this function, here it is, 1 over x, where is it not continuous? Well, I clearly see a vertical asymptote at x equals 0, and a vertical asymptote is a non-removable discontinuity. So that's what's happening in this graph. Everywhere else it's continuous. Let's just pick a point like 1, for example, right? Why am I continuous at 1? Because the function exists at 1. The limit exists at 1. And there are the previous two answers, the function and the limit, both are the same number, 1. So at 1, I am continuous, but I am not continuous at 0 because of a non-removable discontinuity. Here's another example. In this example, we're looking at where is there a discontinuity? Well, I clearly see a hole at x equals 1, and that is a removable discontinuity. So here the limit does exist. The limit exists at 2, but the function does not exist. So the limit exists, the function doesn't exist. That creates a hole, and that is called a removable discontinuity. Everywhere else on this graph, I am continuous. Here's another one. This is a piecewise function. If I'm less than 0, I want to use the function x plus 1. If I'm greater than 0, I'm going to use the function x squared plus 1. And if I'm looking at this graph, heck, I don't see any problems whatsoever. So this graph is continuous over the entire domain, negative infinity to infinity. This graph is continuous. The most important part you got to check of a piecewise function is the transition point. 0 is the transition point because 0 is where I transition from graph 1 to graph 2. And the most important thing is to be continuous at that transition point, your graphs must come together. So all you got to do is plug in 0 to the first function and you get 1. Plug in 0 to the second function, you also get 1, proving that at that transition point, the two functions are coming together, making it continuous. All right, here's another one. This is a sine function. And here we are also continuous everywhere, right? I don't see any problems anywhere. I don't see any holes. I don't see any vertical asymptotes. I don't see any jump gaps. It is continuous everywhere. For example, if I picked pi right there, at pi, I am continuous. Why am I continuous? Because the function exists at 0. The limit exists at 0, and the answers to those previous two questions were both the same, so the limit, so it is continuous at that point. So this graph here of sine is continuous everywhere. All right, let's move on to the second topic of today. This is a very easy one, and this is one-sided limits. So we have already stated this last class, and I'm not changing this, and that is for a limit to exist at a point x equals c, you must approach the same number from both sides. Again, your finger must come together. But we can now take a look at one side at a time. For example, if we add this little plus in the top right-hand corner of the c value, that indicates that for this particular problem, you only care what you approach from the right side. If I add a little minus sign in the upper right corner of the c, that means I only am asking you about what happens as we approach from the left. Now, if I don't have a minus sign or a plus sign, I just have c, well then that is asking you about the overall limit approaching from both sides. But if they're only going from plus or minus, then I'm only looking at one side at a time. So let's look at an example of this. All right, for example, if I ask you what is the limit as x approaches c? Well, I hope that everybody would say does not exist. As I approach c from the left, as I approach c from the right, my fingers, my graph are not coming together. The limit does not exist. But now I could ask you this. What is the limit as x approaches c from the left? So that little minus sign means from the left. Well, from the left, I am approaching, looks like 2.5. And what happens as the limit approaches c from the right? Well, from the right, it looks like I'm approaching, looks very close to 0, maybe 0.1. So from the left, I'm approaching 2.5. From the right, I'm approaching 0.1. And that is exactly why the overall limit does not exist. All right, let's look at this one over here. Let's look at a. What is the limit as x approaches a? Well, I would hope everybody would say does not exist. The right side is going up boundlessly. The left side is going down boundlessly, so the limit does not exist at a. We know that. That's old news. But what happens if so let me write that down, does not exist. But what happens if I said, hey, what is the limit as x approaches a from the left? All right, well, if I approach a from the left, oh boy, I'm not going to any particular number. I'm just going down forever and ever and ever. Okay, so the limit still does not exist, but I could express that maybe a little bit more clear by saying negative infinity. So negative infinity is not a number, so the limit truly does not exist. But since it's going down forever, I can express that answer as negative infinity. And likewise, I'm running out of room here, but as x approaches a from the right, I could give that answer as positive infinity. Now again, positive infinity is not a number, so truly the limit does not exist from the right-hand side or the left-hand side. But since I visually could see what's happening, I could express that answer as infinity or negative infinity. All right, here's another example. If I said to you, what is the limit as x approaches 4? You would say, does not exist. Left side, right side don't come together. But if I changed my writing, I could say, what's the limit as x approaches 4 from the right? Well, as x approaches 4 from the right, my answer is negative 2. What is the limit as x approaches 4 from the left? Well, that answer is negative 3. Boy, my handwriting is getting bad here. Negative 3. So again, you could not have an overall limit, but now we can understand this idea of approaching from the left or approaching from the right. And while we're looking at this graph, let's ask you one more question. Name me the 3 places where the graph is not continuous. Well, at negative 4, the graph is not continuous. That is a non-removable because the limit does not exist, right? That's a jump gap. At negative 1, the limit is not continuous, and that is a hole. That is a removable. That's a a hole that I move down. That is a removable discontinuity. And the graph is also not continuous at positive 4, and that is another jump gap, which is a non-removable discontinuity. Everywhere else, the graph is 100% continuous. It's only those 3 places where I have discontinuities, and make sure you know the different names. All right, guys, pretty easy lesson. Be ready for a quiz next class on this, and make sure you do that homework assignment. All right, talk to you later. See you in the next video.